Our next presenter is Ira P. Victer, who is the Deputy Program Director, RLV X-33 Program at Rockwell International Space Systems Division. Let's give our attention to Ira.
Thank you. One of the things that Eldon mentioned is that the X-33 program has some other uniqueness to it. It's being run under a cooperative agreement. With a cooperative agreement, government gives you an opportunity to use your money. And they encourage us quite a bit in this area. The other aspect, as Mel said, was the cooperative agreement can be canceled by either side at any time. It doesn't make sense as we go through the program. One other unique aspect is that we use the government as a subcontractor. And you'll see this as I go through the presentation. And I know we are to a great extent, and although I'm not sure, but I'm pretty sure that the other teams are. In a partial answer to requirements, the thing that drives the RLP design is the market. The market will determine the commercial viability of this program, including things like the low cost. We're shooting for the numbers as low as $1,000 a pound or less. Performance, we're looking for 12,000 to GEO, 20,000 to the space station, and about 40,000 pounds of lower. Our cargo interface has to be simple. We can't treat cargo the way we're treating it on the space shuttle today. It has to be more like aircraft type operations. It has to have high reliability, just like we're accustomed today on commercial airplanes. We're shooting for 3 nines for the RLV. For routine services and assured access, it takes a considerable amount of time today to get a payload on the shuttle. It cannot happen in a commercial operation. We've looked at the market, and we've looked at it from 3 aspects: today, tomorrow, and the future. And our vision is the future. The future of where we can drive payload costs down. We can introduce payloads and cargo from material processing, for exploration, solar power, tourism. And I think we've heard a lot about that recently. There is a market out there if we could drive the price, the cost per pound down. And the system that we've designed is driven by our business plan. And the 2 aspects of that business plan include the customer needs, as I stated, and also by the investor needs, because without investors to help fund the RLV commercial program, which is going to cost anywhere between $5 and $10 billion. We've got to show an ROI. It has to be an acceptable risk. It has to be cash flow. And we have to demonstrate market capture. Without these elements between the investor and the customer, a commercial program is not viable. And it's the X-33 Phase 2 program that demonstrates such a program. We've chosen as our approach what we call a prudent wing body. And in many ways, you could say it looks like the orbiter today, but really it's not. We have a completely reusable single-stage to orbit approach. And one of the key elements and beauties of it is its structural efficiency. And the tanks, both like the liquid hydrogen and liquid oxygen tanks, are the load carrying. It's simple to manufacture, and the aerodynamics and the aerothermodynamics has been proven on these space shuttles. A lot of the data that we started with has been established. We are seeing no surprises in either area. And it has to be operationally efficient. And I'll talk about that some more. So the SSTORLP design that we've come up with incorporates some new technologies, and you'll see these technologies translated into the X33 program. It's a little over 200 feet long and has a glow of 2.2 million and a dry weight of a little over 200,000 pounds. The important part is mass fraction is slightly under 0.9, but we're also carrying a significant weight margin along with it. It will be powered by 6 RS-2100s, which is a Rocketdyne engine. It's an improved version of the current SSME. And the SSME, which carries a thruster weight of about 56, 57. We feel confident that we could achieve 75 on this new approach. It'll be a highly reliable engine and a lot easier to maintain in the field. Now, the architecture that we've chosen for the X33 was chosen to validate the RLV concept. And we looked at it in 3 areas: the operations area, the flight, and ground. And in each area structured our program so that there's traceability to the RLV. And this traceability occurs in several areas. It's about half scale. The aerodynamics is completely traceable. We have the same aero surfaces, tail elbows, etc. We're using the same materials, both in the structure and the TPS, as we will ultimately use on the RLV. And the configuration of the X33 that has evolved has a gross liftoff weight of about 300,000 pounds, an empty weight of about 70,000. It has a single SSME Block 2 engine, and this was chosen because of its reliability and the demonstrations that could take place with that engine in terms of operability. In comparing the 3 vehicles, look at the current SPS stack, which is about 184 feet long, and you can see the comparison between the RLV and the X33. The X33 is about close to the size of the existing orbiter. We've done considerable work on the X33 to complete a program in the time allotted to fly in 32 months. You must have a running start. We're employing a system called Katia, which I'm sure many of you are familiar with, which gives us an integrated single database. And from this, we've eliminated all mock-ups or models in terms of the determining the physical characteristics, it's all done electronically. And we're at a point now that we have, we're very confident in our preliminary design. We located and sized the structure, and we're ready to go on the X-33 program in terms of the design of the vehicle. And our team is proven. We have several divisions of Rockwell, our space systems division, which will be handling the oxygen tank and the forward fuselage. Northrop is involved with us as a team member, and we'll be doing the wing and the inner tank structure. And our Tulsa division will be doing the hydrogen tank and the tail as the primary areas. We've also engaged some premier companies in the ground systems area. Our own space systems division, Praxair, who's giving us a turnkey operation for both hydrogen and oxygen supplies at the pad, and the Russian outfit in Moscow called the Design Bureau for Transport Manufacturing, DBTM. I haven't memorized that yet, excuse me. But they have, they're the launch service or the launch design facility for the Zenit. And they have some automated launch systems, including umbilicals, that fit right into a program like ours. It's incredible when you see their approach, and the only person that's out with the vehicle is someone to shoot the birds off the track as it's being pulled off. The flight vehicles being pulled out to the launch pad. Our flight test program will be held at Edwards, and we see a series of functional check flights, strip that will be within the confines of the field itself. We'll be going low speed, not too high, just checking out that the vehicle can see. We'll see how it goes. We'll continue with verification flights, and these will be a lot more aggressive. Our vehicle will fly at greater than Mach 15, and that flight will take us up to Malmstrom Air Force Base. And other potentials are to go to Michaels and also over to Holland. We have a flight test program planned of more than 15 flights, and will be, as required by the cooperative agreement, 2 of these will be at Mach numbers of greater than Mach 15. A little more detail on the overall schedule. As Bill said, we're going to fly in March of '99. Phase 2 will culminate in a decision by the end of '99 whether to proceed with the commercial development. We've had a series of user expo, or we've had one user expo, but are planning a series of these. And here we brought the users of the vehicle together and heard what they have to say, what their requirements are, what they would like to see in the vehicle. And it was an outstanding success. We plan to hold these on a yearly basis. Some of the exciting things that have come out of our program are the technologies. I'm going to touch on a few of those. It involves our TPS, our tankage, the IPTD, which is the Integrated Propulsion Technology Demonstration. We built a lot of thrust structure, a lot of composite structure, and I'll share some of those with you. In using aluminum lithium, the easy way to join that is the fusion welding. We've been developing a new process called friction stir welding. And this is a process that was initially developed in England by the Welding Institute. We've picked up on it and have been working on it for several years. It's a joining process. It's not welding, but you plasticize the material and it flows together. It's getting us near zero defect in joints. It's giving us joint allowables that are approaching parent material allowables. And if anyone who has a sense of the criticality of that, it means you save a lot of weight. The exciting thing is the quality of the tank after it's completed. We built one out of 2219 aluminum and the other out of 2195. And our plan is to continue with the 16-foot tank on the X33 out of the same process. In the hydrogen tank area, we fiber placed an 8-foot tank. It's being prepared for testing right now. And it's a seamless tank. It's without a joint. We feel the fewer joints you have in a tank of the size that we're dealing with, the greater chance you have of success for its lifetime. In the wing area, and I apologize for the quality of the picture, this is a full-scale section of an RLV wing. Not an X33 wing, but an RLV wing to the gauges and sizes that we had estimated for that vehicle. It just completed testing at Langley yesterday. We predicted failure load between 101 and 106,000 pounds. It failed at 106,000 pounds. And we're just thrilled that we're able to predict not only the failure, but the onset of buckling in a structure like that. The other area that's just about complete and will be is at Marshall. Today it will be tested for fatigue life starting in about 3 or 4 days. So as Bill said, the contractors have until June 3rd to input these kind of results into the proposal. We're also building a full-scale intertank structure at Northrop. This is a composite structure, very lightweight, 32 foot in diameter, and the section you see there is a quarter of it. And it will undergo testing in the summer and fall after it's completed. The TPS area has been another of those exciting advances, and having grown up with the shuttle program and lived through the TPS issues and problems that we had to solve on that program and solve them, we've developed advances both in the tile and the blanket. In the tile, we have a new kind of impregnation coating where it's several orders of magnitude more durable than the present shuttle pod. We've flown them on the shuttle in the base heat shield area, and it's hard to see there, but there's some black tile on your far right-hand side that have not been pink, and all the tile around it show white dots. And the new tile survived that environment. The other exciting thing is we've flown tile and blankets on the F-15 in a rain at 500 knots. It took paint off the F-15 skin. Tiles survived. And that's, to me, some tremendous advances from shuttle type applications early on. Okay, and in closing, we have a vision of the frequent and routine use of space. There's a tremendous challenge out there. We think the RLV is the right solution. We feel confident we can make it work. And as I shared with you some of the exciting achievements that we've had in technology give us that kind of confidence. And we're making a commitment. We're making major investments in this program, and Rockwell has been solidly behind it. Thank you.
Yeah, you had a flight, Remark 15 flight, something like the landing other networks. How are you getting it back?
We're going to ferry it on the shuttle carrier aircraft. Because of our size similarity, we have the exact same interfaces.
The vehicle is essentially half the cost equation. What analysis has been done on the manpower side, the operational side?
I'll say that we've done extensive analysis that shows it will be economical to operate. I'm not evading the question, but you have to understand that the competition is still on. And I know that TK is writing like crazy, but was not writing down that. So, but in a few weeks, we'll be able to divulge our whole operational approach.
Was any consideration given to so-called mixed motor tri-component propulsion?
Yeah, we traded that off early in the program and decided it was not a viable approach. And we've been concentrating on the liquid hydrogen and oxygen. By the way, we use a densified approach, as I think you saw in one of the charts.
What does Mach 15 sound like from the ground?
That's a good question. Maybe you can help me with it. Boom!
That's a government responsibility. I'll take that. The vehicle will hit those velocities well above the atmosphere, basically in free space. There will be no sonic boom associated with the vehicle at those velocities. The vehicle will, however, lay down a sonic boom. It will easily be doing Mach 4, Mach 5 in the atmosphere. It will sound a lot like the shuttle sounds coming in over Los Angeles.
One about the aerodynamics of the shuttle is very studied, wings and Japan. So it's really not designed for atmospheric flight, only re-entry back to the Earth. Is that correct? Yes. So it really makes a flight from one place to another, and we'll go out to space and return.
Not out to space, no. We can do turnarounds and return to launch site just like the shuttle was able to do. So we're not restricted to a straight flight by any means.
I'm not talking about strictly vehicles to be used to go Earth to do mission in space and return back. It's not to be used as a form of transport from one place to another place.
That's correct. Yes.
Okay.
One more question.
Does it carry as much as the shuttle does or more?
We'll carry 40,000 pounds to low Earth orbit. Our market analysis has said that that plus the 12,000 from GEO should capture greater than 90% of the market. A shuttle could carry something larger. Okay, I think.